I wanted to talk about specifically one of the challenges with change detection that we've come across over the last few years, and one that I think we get a lot of questions about. And this is, if someone gets a LiDAR data set and they get an area reflown, they automatically think that they can just take it into GCD and do a Department of Defense and get an answer out of it. And there are some, there's some challenges with some of these data sets. And one of the biggest problems that we come across is the fact that the data are in different reference frames. And, implicitly when we're doing change detection, we're assuming that they're realized in the same coordinate frame. And if we do a difference between them, anything we see in the difference should be the change that we're looking at. The reality is almost every LiDAR, two LiDAR data sets are probably referenced to a slightly different reference frame. The choice of the reference frame is a little bit project dependent. So when you are maybe getting data from the state government or from FEMA or something like that, their choice of a reference frame is probably different from what, for example, NCOM would typically deliver on a research project. It's complicated enough in the US. It gets even actually worse when we go internationally, because then you're even less familiar with what the choices of the reference frames may have been. For today, I'm just going to focus on the problem in the continental US, maybe a little of Alaska too. So let's start vertically. So if you look in the vertical direction and you look at most of the state governments or federal government collects, and stop me if I'm wrong here, Jason, but most of them will present heights in orthometric height, NAVD 88, North American Vertical Datum of 1988. And this is a height above mean sea level as determined by tide gauges set up around the US. This is the model where, the NGS has spent a lot of money putting in height benchmarks all over the US, and they're all tied to NAVD 88 heights. And so when someone like FEMA does flood maps, they have to have their height information in that version. In a lot of research collections, we tend to not make any height assumptions, and so we will just leave the height in the GPS coordinate frame, which is an ellipsoidal heights. And in theory, conversion between the two is really quite simple. The National Geodetic Survey has high-resolution geoid models that allow you to convert ellipsoidal to NAVD 88 height. Perfect, so it should be easy. Problem is, to date, there are 5 different geoid models. So you have Geoid 99, 03, 06, 09, and 12. There's also a 12A and a 12B. A lot of times, the commercial product will only give you it's an NAVD 88 height. They won't tell you how they got there. If it's a LiDAR data set, they started at ellipsoidal. They used a high-resolution geoid model to get it to NAVD 88. But sometimes they don't tell you. So sometimes you have to kind of infer from the date of collection. These geoid models down here, the numbers at the end correspond to when the NGS adopted them. So 1999, 2006, 2009. So sometimes if your data set was flown in, say, 2007, then you would probably guess, okay, it's maybe the 06 if you're in Alaska, or if it was 2007 and it's in the continental US, it's probably the Geoid 03 model. Sometimes they'll be given, but sometimes they are not. How big is this geoid difference? And this is, first time you do a difference, if you come out and if you're in California and your DEMs are 30 meters different, that's because one's an ellipsoidal and one's an NAVD 88. So there's this map on the NGS website, but if you ever have a large difference between the two of them, this would be the first thing I would look at. Kind of go to this map, see what the difference, kind of Continental US, it's anywhere from 10 to 30 meters in difference. And that tells you that to one of the data sets, you're going to have to apply a geoid model to get them to fit. Now, the second part of this is, does the geoid model matter? Which, you know, does it matter if I use the 99 or the 03 or what have you? And so, to give you an idea, I have 2 points here. So this is a UNAVCO Plate Boundary Observatory point, PO41, which at Marshall Field, which is just up the road here a couple of miles. And then the second one, there's another PBO site, but this one's in Alaska, AC48. So for each of these, I've used the NGS tool to compute a geoid height. And so if we look at the one at Marshall Field here, 99, we go from 16.178 to maybe 16.254. So 8 centimeters different. Kind of debatable whether or not that would be in the noise of the LiDAR data. Not much of a change. But if we look over at the Alaskan point, if we use 99, it's 13.515, and if we use 12, it's 11.5. You'll notice this Geoid 06 was an update only for Alaska. Basically, the geoid models were so crappy for Alaska back here that they did some special campaigns between 2000 and 2005 to try to improve the geoid accuracy up in Alaska. But if, in this case, if you apply the wrong geoid model, you could add two meters of extra difference there that's really not there. Continental US, this is probably one of the better points. In general, the more mountainous and more remote a point is, the larger the potential for differences in the geoid model. If you're in Kansas, no one in here does any work in Kansas, but if you're in Kansas, your geoid model is going to change by a couple of centimeters. It's nice and flat and very well defined. If you're working up near Pikes Peak, you would probably expect to see maybe 30 or 40 centimeters of changes in the model. And the reason for this is the resolution of the geoid model is dependent upon gravity observations. Gravity observations tend to be in areas that are very easy to get equipment to. So Alaska is one that doesn't have a lot of data. Puerto Rico does not either. So the effect is still significant for high accuracy differencing. So even if the geoid model gets you close, there could still be a small bias in your result if you haven't applied the right model. However, you know, if you see a 30 meter difference, you're probably not going to ignore it. So you're going to do something to get rid of that. Where problems really significantly come in is on the reference frame side of things. So typically, if you have FEMA or state government work, they tie their surveys to the National Geodetic Survey reference frame. Current realization is the NAD model, NAD 83. There's a number of variations of these, but for LiDAR, you're really talking NAD 83 Cores 96 or NAD 83 2011. So again, this is a 1996 adjustment. This is the 2011 adjustment. For whatever reason, research data sets that NCOM and others normally do, we usually use the International Terrestrial Reference Frame. And this frame has even more realizations. There really is the difference in the reference frame from 94 to 2014 is like on the order of 10 to 15 centimeters globally. So it's not going to cause that much of a difference. So what's the main difference between the two? There's lots of subtle differences, but the biggest one is that NAD 83 is fixed to the North American plate. So it assumes that North America is its own coordinate system, and it has reference points on it that define a datum that moves along with the plate. Not sure if you guys are aware of this, but apparently the Earth is made up of these tectonic plates that are moving for some reason. I think it causes earthquakes or something like that. Rowan, is that right? Yeah. For ITRF, they actually consider the plate motion, and they also consider horizontal velocities for each of the points. So for ITRF, not only the reference frame is important, but also the epoch that that reference is tied to. So if you have ITRF 2014, and you had a survey done in 2014 and 2018, what will happen is the 2014 will probably be tied to an epoch in 2014. The 2018 will be tied to the epoch in 2018, and depending on the station velocity, those two will be different by, could be centimeters, could be decimeters, depending upon where you are on the plates, because you know they move. And so for ITRF differences, it's important to look at the reference epoch, and unfortunately, it's not published a lot of times. What is normally done for most commercial surveys or most LiDAR surveys is PBO station. This is, so I'll give you NCOM's typical. We will use GPS in the project site, but we will tie them to local PBO or core stations, and we will use the date of the survey as the reference epoch. So if it was January 1st, 2014, the reference epoch would be 2014.0, basically. If we then came back and did the same thing in 2018, on June 1st, it would be, the reference epoch would be 2018.5, or halfway through the year. PBO doesn't publish coordinates for their points, so we do solutions on those days, and that's why we try to keep that day consistent so that you know exactly when it was captured. Problem is, the size of these reference differences are kind of getting down close to the detection level in some of the LiDAR surveys. So this is, again, this point in Marshall Field, and I have taken that and I've computed coordinates for that point, or I've used coordinates for that point in 4 different reference frames. ITRF 2000, ITRF 2008 with a 2005 epoch, cores 96, NAT 83, and NAT 83 2011. And you can see the differences are all under a meter. And so these are actually the ones that are really scary to look at, because they're small enough that you probably wouldn't notice them on the first level, but they would cause significant differences which you might interpret as change kind of near the noise level of the data set. And so the takeaway here is that you really need to, before you do these differences, make sure the Geoid model is correct for sure, but also confirm that the two systems are given in the same reference frame or the same datum. I use those two terms interchangeably. Reference frame means theoretical, there's no points on the ground. Datum is a physical realization. So once I put a point on the ground and assign a coordinate to it, that defines the datum. And that datum is based on a reference frame, which is just a model. So where do you get these differences? Well, fortunately, the National Geodetic Survey provides some tools for doing this. So for the Geoid models, if you go to ngs.noaa.gov, they provide tools that allow you to determine geoid heights in all of these different geoid models. Problem is, they don't allow you to like take a LAS file and upload it to their site and have it change for you. So you have to do something external to that. So there are some other tools. I won't go into those today, but just be aware that you can compute the differences here, but you can't directly apply it to the LiDAR data. For the datum differences, NGS also provides something called HTDP, which is horizontal time-dependent positioning. So if you know the reference frame that was used for your old data and for your new data, you can go to HTDP, plug in those two datums, and it will tell you what delta X, delta Y, delta Z you need to apply to make them coincident. So then it just becomes simply an XYZ shift of the whole data set. to have it in the same reference frame. Of course, the crux is actually determining the datum in Geoid used for legacy data sets. So as an example, when Ramon and I were working on the El Mayor Cucapá earthquake, my Spanish was not so good, I couldn't read their notes, so I eventually convinced them to give me the raw data, and I just reprocessed all of the GPS to put it in a reference frame that I knew. Sometimes you have to actually call the state agency, and I know it's, you know, something a lot of people don't want to do, but you have to talk to like the state surveyor, and he'll tell you what datum it might have been in. They talk a different language and what have you. So, but it takes a little bit of detective work. From an NCOM perspective, I would say the last 10 years worth of data, maybe 2006, 2007, we have done a better job of exactly documenting what that reference frame is. Some of our older data sets, unfortunately, I think we were just excited to have high resolution point clouds out there, and so we delivered without the thought of, hey, someone might actually need to difference these in some point. So if you can't run across an NCOM 1 and you have questions about it, please give me an email, and I'd be happy to dig into it and see what our guys have done for that data set. So switching gears a little bit, I wanted to introduce what I'm going to be talking about in terms of change detection. And so I'm going to be discussing a technique called PIV, or particle image velocimetry. And this technique has nothing to do with determining topographic change. It is actually developed in fluid dynamics to track particles seated in fluid. So you want to look at turbulent flow, you put a whole bunch of particulate in, and you take a bunch of high-speed pictures of that particulate, and you want to track how those particles move so you can get an idea of how the turbulent flow is progressing. And so they have kind of some terms that they use within there. The piece of software that we're going to be using in MATLAB, PIV Lab, was actually part of a PhD thesis that was developed by a student who wanted to track the flapping of bird wings, which has nothing to do with the glacier that we'll be looking at. Oh, there we go. This may be hard to see here, but this is a typical example. We've got a nozzle and they're extracting some particulate in it, and you can see it kind of propagating through time. And so what you get is a sequence of these kind of grayscale images like this, and PIV is used to detect how each one of these little particles is moving in a very quick time frame in between them. So you get some sort of vector diagram that shows, I think this is supposed to play a movie too. Shows how the particles are moving with respect to time. So you have this stack of images that you're looking at. For our purposes, we're only going to have two images. We're going to have a 2001 data set and a 2014, and we're going to determine one set of vectors in between the two of them. So obviously the LiDAR does not have nice little particles in it that we can track. It would be nice if someone would maybe gone out in 2001 and put down some like small black balls on the glacier, but that didn't happen. So what we're really doing is we're taking the data and we're rasterizing it in 2D and using elevation as our particles. And so if we have roughness, we won't bother to try to define what roughness is here, just some amorphous quantity. But if we have some roughness, we can track that through time like it was a particle. So we have to do some sort of rasterization to the point cloud prior to running PIV. We'll talk a little bit about how you do that rasterization, and then a little bit about the algorithm itself that actually is used to do PIV. Yeah.
I hate to be pedantic, but I think it's a good point for people who aren't familiar that PIV actually does not trace the movement of individual particles.
The other thing is that this technique is not probably appropriate for all different scenes. Really, what you're looking at here is, do you have features in the terrain that are moving but can be, look the same in the two data sets? If you had a landslide where, you didn't have virgin soil before, and the soil fell down the hill, you couldn't really use PIV to look at that. You have to have features that you can see both before and after. And so, the glacier that we're looking at is one particular example of this, because it moves quite slow, but it has crests that don't really change their shape very much because of the environment they're in. This technique's used a lot on glaciers. It actually works decently for earthquakes as well, as long as you don't have too significant a deformation, because there will be topographic features that are persistent from before and after the earthquake as well. So we'll get into more details there at 3, but for now I think I'll pass things over to Chelsea to talk about ICP, I think.